We'll look at some numerical examples with related rates problems now, and also how parametric equations can be used with related rates. We look at animations, so we understand that when area changes, radius changes, or when the height changes, the volume changes, and so on. Various related rates will be used, and every time we use the chain rule, dVdt is dVdr times dr dt when the volume varies with time and the radius varies with time. Or when we have area and radius, area varies with time and radius varies with time. These related rates are used for parametric equations. If we know y as the function of t and x as the function of t, we use those related rates to find the y, the x. Our first problem will be that we have a rock dropped into a pond, thus generating an expanding ripple. We know that the radius of the ripple changes at 3 centimeters per second, is getting bigger and bigger. And we want to find how the area changes. So radius is A, the r dt is 3, it's positive because it's increasing, and we wish to find the A dt. Let's draw our diagram, A radius, and connect the variables. Area of a circle is pi r squared. Radius changes, dr dt is 3. Area change, the ADR is 2 pi r when we differentiate this function. We use the related rates, the ADT equals the ADR times dr dt. So we found that the ADR was 2 pi r, and we know that dr dt is 3, and radius is 8 at the instant when we want to find the ADT. So it's 2 pi times 8 times 3, which is 48 pi. That's the exact answer which is required. Area will be centimeters squared per second. Now we have a sphere, and it is dissolving, melting, so it is getting smaller and smaller. And the radius is decreasing at a rate of 5 centimeters per hour, getting smaller. We assume that it still maintains a spherical shape. So we try to find dVdt when the radius is 2 centimeters, knowing that the radius is decreasing at this rate. Now the rate is negative because it's getting smaller and smaller. The relationship between the volume of a sphere and the radius is given on your formula booklet, 4 on 3 pi r cubed. We differentiate this expression to substitute into our related rates. So dVdr is 4 on 3 pi times 3 r squared, which simplifies to 4 pi r squared. So dVdt is 4 pi r squared times negative 5, and we want to find it when radius is 2. So substitute 2 for radius, and the exact answer is minus 80 pi, or answer correct to 1 to the nearest centimeter cubed is minus 251. The unit is cubic centimeters per hour because we're looking at the change in the volume. Now, we have a conical pile of sand, and more sand is being dropped onto the top. The height of this conical pile is increasing at the rate 0.5 centimeters per minute, and we want to find the rate at which the sand is being poured at the instant when height is 4 centimeters. So, we need to start by finding volume of the cone in terms of the height only. How could that be done? If this angle is 90, that means half angle is 45 degrees. If that's 45, that's 45. That means that h height is equal to the radius. Okay? So if h at any time is equal to the radius, we replace r with h, and the volume of a cone, 1/3 pi r squared h, becomes 1/3 pi h cubed. If we differentiate this function, 3 times 1/3, 1 pi h squared. We use related rates dv dt is dh times dh dt. We know dv dh is this, and dh dt was given in the question. That simplifies to pi h squared on 2. Substitute 4 for height, and we get dv dt is 8 pi cubic centimeters per minute. Ladder problem. The ladder is sliding down the wall. So if y is getting smaller and smaller, x is getting bigger and bigger. We'll assume that the y-axis goes vertically up and the x-axis goes to the left. The related rates here need to connect y, x, and the length. So, using Pythagoras, x squared plus y squared is 64. We make y the subject, square root 64 minus x squared. In our related rates, we need to find dy dx. So we need to differentiate here dy dx. Chain rule, derivative of square roots 1 on 2 square roots. Derivative of the inside is minus 2x. 2 and 2 cancels out. So dy dx becomes this expression. Now, related rates, because we assumed y was pointing up and the ladder is sliding down, therefore dy dt is negative. So we put negative 0.4 for dy dt. This is our dy dx, and we are looking for dx dt. Rearrange the equation. Dx dt is this expression, and we wish to find it when x equals 3. So we replace x with 3. 64 minus 9 is 55. That's the exact answer, or 0.989 centimeters per second to 3 decimal places. Parametric equations problems. A curve has parametric equations. X is 2t plus sine 2t and y is cos 2t. Find dy dx. The related rates used is dy dt is dy dx times dx dt, but we want to find dy dx, so we need to rearrange the equation. All we need to find now is dx dt and dy dt. Differentiate that, 2 plus 2 sine cos plus 2 cos 2t, derivative here is minus 2 sine 2t, and we substitute those two derivatives into dy dx, and 2's cancel out. So dy dx is minus sine 2t over 1 plus cos 2t. So that's one of the examples from the textbook, how to find dy dx given x as the function of t and y as the function of t. Similar example, again we have two parametric equations, x as the function of t and y as the function of t. Find the equation of the tangent to the curve when t equals pi on 6. So we start in a similar manner. Dy dt is dy dx times dx dt. We find dy dx as dy dt on dx dt. We differentiate 1 plus sine t and cos t. This time we wish to find the values of those derivatives when t equals pi on 6. 1 plus sine pi on 6 is 1 plus a half is 3/2. dy dt is cos pi on 6, which is root 3 on 2. Substitute here. So dy dx root 3 on 2 on 3 on 2 is root 3 on 3. That's our gradient of the tangent. Now we need to find the x and y value for this particular value of the parameter t. When t is pi on 6, x is pi on 6 minus cos pi on 6, which is root 3 on 2. And y is sine pi on 6, which is a half. So now we use the equation y minus y1 is m of the gradient x minus x1 and simplify to this form. There is an example in a textbook finding the second derivative with parametric equations. I don't think you will get a question like that. It's very complicated. You might have a look at that, but I never saw a question on second derivative with parametric equations on the exam. So what I would like you to do, read some more examples, 18 to 24 on those pages. Try the listed questions and also go to Edrolo and try to watch that again. Make sure that you understand related rates. If there are any questions, please email me and ask for some more clarification.